All right, so this is actually pretty surprising. We have a security RCE in OpenSSH going on here. CSV was filed. This is CVE 2024 6387. Are you ready for some remote code execution? OpenSSH. Let's go. Preliminary note, OpenSSH is one of the most secure software in the world. This vulnerability is one slip-up in an otherwise near-flawless implementation. Its defense, in-depth design, and code are a model and an inspiration, and we should thank OpenSSH's developers for their exemplary work. Agreed. Absolutely. We discovered a vulnerability, a signal handler race condition, in OpenSSH's server, SSHD. If a client does not authenticate within login grace time seconds, 120 by default, 600 in old OpenSSH versions, then SSHD's SIG alarm handler is called asynchronously. But this signal handler calls various functions that are not async signal safe. For example, syslog. This race condition affects SSHD in its default configuration. Oh man, this is one of those attacks that are just crazy. These are one of those attacks that I just don't even have the skills to understand, but let's go through. Let's see what we got here. Our investigation, we realized that this vulnerability is in fact a regression of CVE 2006-5051. Signal handler race condition in OpenSSH before 4.4 allows remote attackers to cause a denial of service, crash, and possibly known execute arbitrary code. This was reported in 2006 by Mark Dowd. Oh man. All right, we're getting deep here. This regression was introduced in October 2020, OpenSSH 8.5p1 by commit this, revised log infrastructure for OpenSSH, which accidentally removed an if-def do log safe in SIGHAND from SIGDIE, a function that is directly called in SSHD's SIG alarm handler. In other words, OpenSSH before 4.1 or 4.4p1 is vulnerable to the signal handler race condition, if not backport patched against CV 2006-5051, or not patched against CV 2008-4109, which was an incorrect fix for 2006-5051. Wow. 4.4p1 less than OpenSSH and up to 8.5p1 is not vulnerable to the signal handler race condition because the if-def do log safe in SIGHAND, which is SIG handler, by the way. I know things. That was added to SIGDIE by this patch for 2006-5051 transformed this unsafe function into a safe exit one call. Everything that's less than this, everything between these two is vulnerable again to the signal handler race condition because of the if-def do log safe SIGHAND was accidentally removed from SIGDIE. Oh, so 9.8 is fine. Are they saying this must have been that responsible disclosure? This vulnerability is exploited remotely on glibc-based Linux systems where syslog itself calls async signal unsafe function, for example, malloc and free, an unauthenticated remote code execution as root because it affects SSHD's privilege code, which is not sandbox and runs with full privileges. We have not investigated any other libc or operating system, but OpenBSD is notably not vulnerable because its SIG alarm handler calls syslog R, an asynchronous signal safer version of syslog, which was invented by BSD in 2001. Okay, I want to see some examples here. I think we see what's happening here. OpenBSD Chad, yep. Okay, security vulnerability introduced by unnecessary complexity. I'm not sure if it's unnecessary complexity. It sounds like it's perfect complexity, right? When you're unable to be logged in after the timeout period, you go into this little logging thing, and then you die, and then somebody removed an if-def for when you're in a specific case, and then this causes a problem. Nevertheless, we immediately faced three major problems. From a theoretical point of view, we must find a useful code path that, if interrupted at the right time by SIG alarm, leaves SSHD in an inconsistent state, and we must then exploit this inconsistent state instead of SIG alarm handler. Is this... Okay, so what I'm now reading is this is a theoretical bug, not a practical boots on the ground bug. Is that safe to say? Because we've been hearing a lot about this, where we get a ton of a lot of open source things are getting a ton of information in which may or may not be super useful. From a practical point of view, we must find a way to reach this useful code path in SSHD and maximize our chances of interrupting it at the right time. From a timing point of view, we must find a way to further increase our chances of interrupting this useful code path at the right time remotely. All right, so let's see. I just checked Ubuntu 2204 and 2404, and they are using SSH version 8.9. which is 9.8 or 8.9. Okay, so this sounds like it may not be as big of a problem as we see. We may not be able to take advantage of it. Okay, 8.9. So in other words, 2204 and 2404 both are technically vulnerable to this bug. To focus on these three problems without having to immediately fight against all modern operating system protections, in particular ASLR and NX, we decided to exploit old OpenSSH versions first on i386, and then, based on that experience, recent versions. First, SSH 2.0, OpenSSH 3.4p1, Debian 3.1, okay, a lot of this, Woody, from this one right here. This is the first Debian version that has privilege separation enabled by default and that is patched against all critical vulnerabilities of that era. All right. To remotely exploit this version, we interrupt a call to free with a SIG alarm inside SSHD's public key parsing code. Then leave the heap in an inconsistent state and exploit this inconsistent state during another call to free inside SIG alarm handler. Our experiments takes 10,000 tries on average to win this race condition. Oh, okay. So it's not purely theoretical. They are able to do it on the older versions. Okay. With 10 connections, max startups accepted per 600 seconds, it takes 1 week on average to obtain a remote root shell. Okay, I mean, that's still real. That's definitely real. I mean, this is obviously a very old version of it, right? Because they said Debian version Woody. I don't even know what version Woody is, but Woody had to be a long time ago. Second, SSH 2.0, this big thing right here from Ubuntu, this big thing. This is the last Ubuntu version that still had vulnerable to 2006 5051 signal handler race condition, right? So this is before 4.4. So this is before 2006. To remotely exploit this version, we interrupt a call to PAM start with SIG alarm, leave one PAM's instructions in an inconsistent state, and exploit inconsistent state during a call to PAM end inside a SIG alarm handler. Our experiments, it takes 10,000 tries on average to win this race condition, i.e. 10 connections. Okay, and at 120 seconds, it takes 1 to 2 days to remain a remote shell. Okay. All right, here we go. We're on this version of Debian. This is the current Debian stable version, and it is vulnerable to the regression of CV 2006-5055. To remotely exploit this version, we interrupt a call to malloc with SIG alarm inside SSHD's public key parsing code, leave the heap in an inconsistent state, and exploit this inconsistent state during another call to malloc inside SIG alarm handler, more precisely inside syslog. In our experiments, it takes up to 10,000 tries on average to win this race condition, so 3 to 4 hours with 100 connections. Max startups accepted 120 seconds. Ultimately, it takes 6 to 8 hours on average to obtain a remote shell because we can only guess the glibc's address correctly half of the time. ASLR is where they effectively take in-program memory pointers and sanitize them, right? This is definitely not this is no longer theoretical, it sounds like. Right, it randomizes it, right? I know it's randomized, but it's address layout randomization. Yeah, okay. That's what I thought. Okay. Address space layout randomization. Yes, I've heard about this. I've heard about this thing. I'm just a dumb programmer, aren't we all? This research is still a work in progress. We have targeted virtual machines only, not bare metal servers, on a mostly stable networked link, 10 milliseconds packet jitter. Okay, so not a lot of time right here. We are convinced that various aspects of our exploits can greatly improve. We have started to work on an AMD 64 exploit, which is much harder because of the stronger ASLR. Interesting. A few days after we started our work on AMD 64, we noticed the following bug report in OpenSSH Bugzilla about deadlock in SSHD's SIG alarm handler. All right. We therefore decided to contact OpenSSH's developers immediately to let them know that this deadlock is caused by an exploitable vulnerability. We put our AMD work on hold and we started to write this advisory. This is actually pretty cool. This is actually really, really wild. So this is from 2005 version, theory. I do like that they have a little quote every single time. They have a little quote upon every single little section. Okay, theory. But that's not like me. I'm breaking free. The interrupters. Okay, what are the interrupters? I don't know this reference. I assumed it was a band. Yeah, it is. New album. Completely reasonable. I knew it. All right. The SIG alarm handler of this OpenSSH version calls packet close, which calls buffer free, which calls X free, and hence free, which is not async signal safe. Okay. So Grace alarm handler. Dang. Man, what a code. What a code threading going on here. So you have to hit it. You have to hit a signal, some sort of signal, while calling this. So that's why it takes like 1 in 10,000 tries, because you're trying to do a timing attack. And that's why it was so important where they mentioned packet distribution, right? So a big thing about packet distribution is often you'll see something like that, right? Where, whoopsies, that was a terrible one. I hit my mouse next to me, right? Where you're going to see something like this, right? This is a 0 over here, which virtually no packets go right here. And then you have really fast packets. Then you have the majority of packets landing right here. And then you have this really long tail of possible packets. So for you to be able to cause this SIGINT, you have to land sending packets. My assumption is that they have the 120 seconds as when it's closing. They use that as a means to try to time out packets being sent to hit this. And that's why it only works with default configuration, because they can figure out that. I guess you could technically run enough sessions, you can figure out the configuration, you can figure out the default or the configuration for timeouts. I assume this is how they're doing it. And so if you send a packet, if you expect close down to happen in 120 seconds, and you're sitting there measuring latency, and latency varies between 10 milliseconds to 100 milliseconds, you're trying to land a packet, is my assumption of what's going on here, is you're trying to land a packet right here at this perfect moment. I think that's what they're trying to say. So that way it's calling and it's being interrupted during the middle of a free. That's way smarter than I am. Yeah, this is vastly outside of my understanding, but I think that's what I'm reading right now. Yeah, dude, it's like seriously way smarter than me. That is incredible research. Consequently, we started to read the malloc code of this Debian's. Dude, when you're reading malloc, you are deep. To see if the first call to free can be interrupted by SIG alarm and exploited during a second call to free. Inside the SIG alarm handler at lines this right here above, because the glibc malloc is not hardened against the unlink technique pioneered by Solar Designer in 2000. We quickly spotted an interesting code path in chunk free. Okay, so we have a malloc, right? So we have our pointer. We have our internal size, all that. If I'm not mistaken, how malloc effectively works in the simplest part is that when you ask for a chunk of memory, it gives you a pointer to this part of the memory, but behind it is a header. And so if you just go to this pointer and walk backwards, you effectively get to the header size, if I'm not mistaken. That's like the basics of how malloc work. That's why when you free a pointer, it knows how to free the pointer, because it has this right here. It effectively has a header hidden behind the memory chunk. All right, so this is just code I don't quite understand here. So we got ourselves a structure. We got ourselves an unlink, which just hits it with the old P. Dude, nothing like a macro. Quick macro unlink with the BK, PK, FD, file descriptor maybe. File descriptor, BK, BK. Yeah, oh, okay, so this is unlinking. Okay, this looks like a two-way. This looks like some sort of linked list going on here, right? Because we have the BK and we have the FD, and we're pointing them at each other. I don't know what it's doing. All right. I can't read this code. I'm not smart enough here. All right, so there we go. Here we go. To exploit this code path, we arranged for SSHD's heap to have the following layout. Are all mallocated chunks of memory. P, S, F, and B are their previous size, size, FD, and BK fields. I don't know what BK stands for. Okay, so you have chunk X, chunk Y, and chunk Z. So how do you arrange the heap to look like this? Is it just sending in 3 packets? It must be sending in 3 packets. Burger King, obviously. Back. BK, back. It's so simple. It's so simple. It's like right there. Burger King. First, if the call to free chunk Y is interrupted by SIG alarm after line this, but before line this, then chunk Y is already marked as free because chunk Z's previous prev in use bit is cleared at line this. Okay, so there must be some sort of arena allocator that's using a linked list to walk the arenas. Is that what it is? But it is not yet linked into the doubly linked list at line 3251. In other words, The chunk-wise FD and or forward, yeah, that's forward and back pointers, still contain user data, attack control data. Okay. Welcome to the arena. Yeah, second, if inside SIG-alarm handler packet close calls free chunk X, then the code block at lines, these ones right here, is entered because Y chunked is marked free and chunk Y is unlinked. And so the so-called AA4BMO primitive, almost arbitrary 4-byte mirrored overwrite. What a name, man! This is wildly low because chunk-wise FD and back or forward and back pointers are still attacker controlled. For more information on the unlinked technique and primitive, check out this one. Okay, so this is the JPEG. Interesting. Now I want to learn more about this. Dang it! I just want to learn about all of them. Last, with the AA4BMO primitive, we overwrite the glibc's free hook function pointer. This old Debian version does not have ASLR nor NX with the addresses of our shellcode in the heap, thus achieving remote code execution during the next call of free. Dang. Okay, so that's why it was so simple to do Woody, is because since you didn't have this, it was really easy to, you could just had a defined address in which was free hook. So you never really had to, okay, so that's why they started on Woody, just to verify that it worked. This makes more sense. For the link, it's right here. Okay, practice. They're taking over. Now they are taking over, and they got complete control. The interrupters. Liberty. Again, beautiful. To mount this attack against SSHD, we interrupted a call to free inside SSHD's parsing code of the DSA public key, i.e., line 144 below is our free chunk Y and exploit it during one of the free calls in packet close. One of the lines 341 to 344 above is our free chunk. Okay. Buffer get big num 2. Damn, I don't even know what's going on here. So buffer get string must be some sort of, here's the buffer. You must get some sort of length that, I'm not even sure what's going on here. Binary to big number, then free bin. Initially, however, we were never able to win this race condition. Interrupt the free call with at line 144. This one right here. Okay, at the right time. Eventually, we realized that we could greatly improve our chances of winning this race condition. The DSA public key parsing code allows us to call free 4 times at lines 704 through 707 below. And furthermore, SSHD allows us to attempt 6 user authentications. If any one of these 24 free calls is interrupted at the right time, then we later achieve remote code execution in SIG-alarm handler. Oh, because it does it like, look at that. It just does it back to back to back to back. Oh, so that's how they're doing it, is they're waiting for the most, like, something that just has such a large chunk of freeze happening that all they have to do is just keep on tossing things in there and interrupt it. Okay. With this improvement, we finally won the race condition after 1 month. Wow. We were happy, and it did a root shell dance. But we also felt that there is still room for improvement. Timing. Don't worry, just wait and see. The interrupters haven't seen the last of me. Therefore, again, I have an absolute love with the fact that they keep quoting a single band called the Interrupters in an attack that it's all about interrupting program flow. This is just so good. I can't imagine, I cannot fathom fighting a race condition for that long. Well, especially since they said the following phrase, that they tried to do this one for a long time and figured out they just couldn't make it happen. So how long was this running where they are trying to interrupt this before they found this and then tried that, which this then ran for 1 month, right? Like, how long has this research been going on? We therefore implemented the following threefold timing strategy. We do not wait until the last moment to send our rather large DSA public key, to SSHD. Instead, we send the entire packet minus 1 byte, the last byte, long before the login grace time. Okay, so, yes, so they're hanging it because it's minus 1 byte, so it's waiting for that last byte before it sends it off as a complete packet. Okay, we're starting to take shape here. And then send off the very last byte at the very last moment to minimize the effects of network delays. Yes, because if you have one packet, there's like this weird thing that happens in networks where one packet is vastly faster than 2 packets. Like the difference between 1 and 2 is vast. I've heard numbers tossed out. You're going to have to get some coding guy from Netflix to talk about this. But he mentioned one time to me that 1 packet versus 2 packets is something along the same lines as 1 packet versus 20. Like the timing difference is not that much difference. It's like vastly different. 1 is extremely fast versus 2 or more is just like a huge window for like problems. I've heard that before too. Yeah, I don't know the exact amount, but I heard there's just a whole problem set once you send more than 1 packet. So this makes perfect sense. If you want to really time the attack, you have a singular packet that you send. We keep track of the median round trip time by regularly sending packets that produce responses from SSHD. Called it. Okay, this makes sense. And keep track of the difference between the moment we are expecting our connection to be closed by SSHD, essentially the moment we receive the first byte of the SSHD banner, plus the login grace time, and the moment our connection is really closed by SSHD according and adjusted our timing, i.e. the moment we send the last byte of our DSA packet. Dang. Okay, so they are trying to, they're literally trying to get something to start running the DSA packet and then using that 120-second login grace time to then interrupt it and call free. Okay. These times are interrupt free call with the SIG handler. With the SIG abort, these time differences allow us to track clock skews and network delays, which show predictable patterns over time. We experimented with linear and spline regressions, but in the end, nothing worked better than simply reusing the most recent measurements. Let's go. That's because, like, I mean, the problem about networks is networks aren't, like, what happened 1 hour ago isn't really an indication of what is going to be happening now. Even what happened 10 minutes ago may not be an indication to what's happening now. Like, there's just so much variation in networks. Possibly deep learning might yield even better results, a Kalman filter. This is left as an exercise for the interested reader. More importantly, we further increased our chances of winning this race condition by slowly adjusting our timing through involuntary feedback from SSHD. If we receive a response, SSH2 message user auth failed to our DSA public key packet, then we sent it too early. SSHD had time to receive our packet in an unprivileged child, parse it, and send it to the privileged child, parse it there, and send the response all the way back to us. If we cannot even send the last byte of our DSA packet, then we waited too long. SSHD received a SIG alarm and closed our connection. If we can send the last byte of our DSA packet and receive no response before SSHD closes our connection, then our timing was reasonably accurate. Interesting. Okay, yeah, because you're not only are you facing network variations, you're also facing CPU stuff. Just assuming that you may have all sorts of different problems, right? What happened if they're in a shared environment? Right, there's all sorts of then variations of timing on top of this. That's crazy. This is crazy. This feedback this is so cool. This feedback allows us to target what we call the large race condition window. Hitting it does not guarantee that we win the race condition, but inside this large window, there are 25 small race windows. It's so smart. Inside the 24 free calls that, if hit, guarantee that we do win the race condition. With these improvements, it takes approximately 10,000 tries on average to win this race condition, i.e. 10 connections, 600 seconds login grace time, 1 week. But the new ones are much smaller. It's only 120 seconds, which cuts it down to 1 to 2 days. All right, theory, take 1. I sleep when the sun starts to rise. The interrupters, alien. The SIG alarm handler of this OpenSSH version does not call packet close anymore. Moreover, this Ubuntu glibc 236 always takes a mandatory lock when entering the functions of the malloc family, even if a single thread, like SSHD, which prevents us from interrupting a call to one of the malloc functions and later exploiting it during another call to these functions. They would always deadlock. We must find another solution. Oh, this is exciting. Hey, I'm going to get a quick, Flip, take this part out. I'm going to get a quick drink of water. Flip, take it out. CVE 2006. I'm just gonna call 20. I'm just gonna call it by the year because it looks like there's one per year, so we should be just fine. So 2006 CVE mentions a double free in GSS API, but GSS API or Cerberus is not enabled by default, so this does not sound very appealing. On the other hand, PAM is enabled by default, and PAM end is called by SSHD SIG alarm handler and is, of course, not async signal safe. We therefore searched we searched for a PAM function that, if interrupted by SIG alarm at the right time, would leave PAM's internal structures in an inconsistent state, exploitable during PAM end. in the SIG alarm handler. And we found PAM set data. All right, what do we got here? So is it the malloc? Is that what they're trying to do? Is they're trying to call during malloc stuff? But I thought all the malloc stuff is thread safe. So it must be something else that I do not understand. If this function is interrupted by SIG alarm after line 66, but before line 74, then the data entry is already linked into PAM's structure, PAM-H, but is cleaned up. Let's see, but its cleanup field, a function pointer, is not yet initialized. Since the malloc on 57 does not initialize its memory, if we are able to control cleanup through leftovers from previous heap allocations, then we can execute arbitrary code when PAM end. Oh, calls PAM free data. So okay, so if I'm reading this correctly, they want to cause the abort to happen here, to call a cleanup somewhere else, but before that happens, this value needs to be set to a specific different function pointer so that when it calls cleanup on the function they control. Okay, clever. I literally have no idea how they set this value. Okay. PAM-free data. Handler TPAM structure. Let's see this one. We have the data equals the data while last. Yep, there it goes. It calls the cleanup. This would have been extremely simple exploit. Unfortunately, we completely overlooked that PAM set data can only be called from PAM modules. If we interrupt it with SIG alarm, then PAM caller is still PAM called from module, in which case PAM end returns immediately without ever calling PAM free data. Back to the drawing board. Okay, theory take 2. Not giving up is not what we do. The interrupters, title holder. We noticed that. Dude, they must have been jamming to the interrupters for months straight. For literal months straight. We noticed that at line 601 below, SSHD passes a pointer to its global SSH PAM handler pointer directly to PAM start, which is called once per connection. Static PAM handle. Shapam handle goes in here. Error. Okay, we set this thing. We therefore decided to look into PAM start itself. If interrupted by SIG alarm, we might leave the structure pointed to by spam handler in an inconsistent state, which could then be exploited inside the SIG alarm handler when PAM end SSH handle or SSH PAM handle, is called. Okay, PAM start. All right, there it is. So there we go. So we have a calloc and we have an init handlers. We have an init handlers, which we read from config file. We have config file, which adds PAM handler. We have add PAM handler, which grabs these handlers, sees if it's authenticated, and we malloc the size of the structure, and we set the next and all. I think I barely understand this code. Dude, I don't know why I'm so bad at reading C. Can we just get this in Zig already? Can we just get this in Zig? At line 32, PAM start immediately sets SSHD's SSH PAM handle to a callocated chunk of memory. This is safe because calloc initializes this memory to 0. That's right. On the other hand, if PAM add handler, which is called multiple times by PAM start, is interrupted by SIG alarm after line 874, but before line 886, then mallocated structure is linked into PAM, but its next field is not yet initialized. If we're able to control next through leftovers from previous heap allocations, then we can pass an arbitrary pointer to free during the call to PAM end. I still don't understand how they pass this arbitrary pointer. That's what confuses me. How do they set it up in such a way that they can do this? Okay, so is it something where they are able to allocate memory from the heap, then they know that this memory is freed, and then they know that this memory is somehow reallocated with something that's smaller, and thus its offset is something they set earlier to point to a certain address? Is that what this is going? It reuses nodders. Okay. So am I understanding this correctly? Because that way, then this handle, because they know the size of this. So if they can just get the correct thing in place here, and then that's how I understand it. Yeah. Yes, people are saying yes, but I think people say yes to whatever I say sometimes. That is kind of where it goes. Yeah. I think sometimes people say yes to whatever I say. No. Yes, they're trying. Yes. Okay, so yes, someone said it correctly. Yes, that's the whole point of the interrupt, is that they're trying to grab the freed memory before it gets clear and redirect it. Yes, they're trying to call a second. They're trying to interrupt during a read or during a free process to leave it in a specific state that would then be called into something remotely. And then if you could just set that address. So my assumption of how this works is that what this is that here, I'm going to redraw this. So this is how this quote unquote works in my head. Let's pretend the size of this thing is like this big and they have a chunk that they could override. So if they can call it before it's freed and then this handler gets called, if they set this address to be like, say, right here, and then this is the actual code execution, right? I just drew an American flag. Fuck yeah, Eagles. Yeah, Eagles, caw, caw. Eagles, hell yeah, look at that eagle, America, yeah, guns. Yeah, this is a shotgun, hell yeah. Yeah. There you go. What the fuck is a kilometer? Right? And so then they execute, then they just effectively offset this into the struct further where they can execute the code. I think that's what I'm understanding, because they also said a rather large DSE encryption. I don't know the encryptions very well. I don't know these things, right? I think that's what I'm seeing or understanding. Well, Malik will get a pointer. Malik will get a pointer to the heap that will not be cleared. So if it has data, it will still be there. Yes. So I think I effectively am understanding how this is working in a very, very, very primitive, childish way. All right. So there you go. See, we call the free handler, and the free handler calls the auxiliary free handler, which then calls this PAM drop. Then we have the mem set. Then we just set a bunch of zeros, and then we last. Okay, so what is going on here? So what is this? Because of the malloc in Ubuntu's libgc already hardened against the old unlink technique, we decided to transform our arbitrary free into a malloc Malefericum's house of mind. This must be some really well-known thing. Is a heap exploitation technique detailed in the malloc Maleficarium document, which is a renowned resource in the field of computer security and exploitation. This document was created in 2005 and explores various methods to exploit GNU-C libraries, glibc, malloc implementation for arbitrary code execution and other malicious activities. The house of the mind technique specifically involves manipulating the program's memory allocation process to write a large value, a heap pointer, to an arbitrary address. This is typically done by exploiting a single byte override to influence the arena handling in glibc's malloc system. The primary goal is to control the arena structure to facilitate further exploitation. However, this technique and several others described in the malloc Maleficarium, I think I'm saying that, Maleficarium, I don't know how to say that word, have been migrated to more recent versions of libc due to integrity checks. Okay. We free our own non-main area chunk, point to our fake arena to SSHD's got PLT. The Ubuntu SSHD has ASLR, but not pi, and overwrite exits entry with the address inside our shellcode in the heap. This Ubuntu's heap is still executable by default. And more information of Malik's okay, right here. Practice. I have learned everything the hard way. The interrupters, the hard way. To mount this attack against SSHD, we initially faced three problems. The house of the mind requires us to store a pointer to our fake arena right here in the heap, but we were able to store attacker-controlled data at such a high address. Because SSHD calls PAM start at the very beginning of the user authentication, we do not control anything except the username itself. Luckily, a username of length 128 KB Who's allowing that? Well, there's your problem. Shorter than the default mmap threshold allows us to store our own data at this address. The size of the field of our fake non-main area chunk must not be too large to pass free security checks, i.e. it must contain null bytes, but our long... Oh, yeah, you contain null bytes to like think that there's nothing left in the string, but our long username is null terminated string that cannot contain null bytes. Luckily, we remember that PAM-free handler's auxiliary zeros the structure that it frees. Yes, right here. We remember reading that one. Okay. Yeah. We therefore patch the size field of our fake chunk with such a memset 0, and only then free it. We must... let's see. Oh, wow. Okay, I'm perplexed at this point of what they're doing. And now I can't understand what's happening. So during the initialization, they set up a fake memory arena by overriding the username due to the hard requirement of the threshold. And then somehow they get it to point in there, in which then they can actually make it so that it looks like it's been faked. And then they can zero out specific parts to make it so that this one doesn't accidentally erase into stuff they don't want to erase into. We must survive several calls to free right here and above before free of our fake non-main area chunk. We transform these frees into no-ops by pointing them to fake is mapped chunks. Free calls munmap chunk, which calls munmap, which fails because these fake is mapped chunks are misaligned, effectively a no-op because assertion failures are not enforced in this Ubuntu's glibc. Yeah, fix. Username can be no longer than 50 characters and shut the hell up. Finally, our long username allows us to control the potentially uninitialized next field of the 20 different structures, although leftovers from temporary copies for our long username. Because PAM start calls PAM add handler multiple times, i.e. our large race window contains 20 small race windows. Timing. The same tricks they used before. The interrupters divide us. I can tell what kind of band the interrupters is based on these little quotes. Okay, I'm getting definitely some anti-flag vibes going on right now. For this attack against you, definitely a punk rock band. I would say the interrupters have to be a punk rock band at this point, just based on this. Some 70s, 80s punk rock band. How do people find this? Depression. Anti-flag, yeah. Ska punk, yeah. He is literally showing you, yeah. Looks like an indie band, okay. Could be indie, yeah, I can see that. For this attack against Ubuntu 6.06, wow, that's old-ass Ubuntu. We simply reuse the timing strategy we used against Debian 3.0R6. It takes 10,000 tries on average to win this race condition with 10 connections, so that's 1 to 2 days. Okay, note, because of this, Ubuntu glibc always takes a mandatory lock when entering a function of malloc family. An unlucky attacker might deadlock all 10 max startup connections before obtaining a root shell. We have not tried to work around this problem because our ultimate goal was to exploit modern OpenSSH anyways. Okay, good. Next section. So this is modern SSH, right? This is okay, so now we're on to modern. Now that you're ready, take the demons head on. Let's go. Let's go, interrupters. What a quote. What a quote. The signal alarm handler to this SSH version does not call packet close nor PAM end. In fact, it only calls one interesting function, syslog. Sigdi, SSH remote IP adder port. Oh, is this SSH remote IP adder the same one of node IP? Do they not know there's the CVE against it? Shut up, don't worry. I'm just being stupid. All right, we got some code. Let's see. Sigdi is a Don't you just love macros? Can we all agree macros are just beautiful? All right. Let's see. SSH sigdi, const char file, const char function, line, show function, all this kind of stuff. Then we do a little log right here. Beautiful. Okay, that just grabs a bunch of these magic macro values. Let's go. SSH login right here. For those that don't know, when you compile, your preprocessor macros get turned into code. __ file __ then gets turned into the literal file name, right? And func gets turned into the literal function name. Line gets turned into literal line number, right? I hope he's being sarcastic. Macros are evil. No, macros are actually evil. I know very little about them because they are just they're gosh darn dang evil, right? They are difficult to deal with. We're gonna do some log. We're gonna do some logs. Let's do some logs. So we got this thing going on here with the format buff. Okay. Our two key questions are: does the syslog of this Debian glibc 236 call async signal unsafe functions as such as malloc and free? And if yes, does this glibc still take a mandatory lock when entering the functions of the malloc family? Luckily for us attackers, the answer to our first question is yes. If and only if the syslog and size sigalarm handler is the very first call to syslog, then local time 64R, which is called by syslog, calls malloc 304 to allocate a file structure at line 166, and then calls malloc 2 to the 12 to allocate the internal read buffer at line 186. Let's go. We got 2 mallocs. Let's go. Local time R. Man, I've never been more scared of mallocs now in my entire lifetime. Oh my gosh. All right, so we got our local time R. We get this thing, a TZ convert, which does this TZ set internal. TZ set internal does this TZ file read. TZ file read does an F open file RCE. Let's go. All right, there we go. Note, because we do not control anything about mallocations. Dude, I love that, mallocations. Nor their order, not their order, not their size, nor their contents. We took RCE at line 166 as a much needed good omen. Dude, sometimes fate is too nice. Sometimes fate is just beautiful, right? You can't even believe it. And luckily for us, the answer to our second question is no. Since October 2017, the glibc's malloc functions do not take any lock anymore since single-threaded when single-threaded like SSHD. So it's a re-entrant bug. Is that what that says to me? Due to the fact that it's single-threaded, it makes the assumption that it can effectively not be interrupted, or you can't have reentrancy. And since you can't have reentrancy, you can use an interrupt to effectively create reentrancy. For those that don't know what reentrancy is, it means that your function effectively can be called while executing, right? So you can imagine you have foo, and foo has a bunch of code that has things being called, and somewhere within foo recalls foo. And so recursion is reentrant effectively. But if you set up state, right? So foo at the very, very top sets up a bunch of state that needs to be unset at the bottom. Effectively, you have code up here, and then you have a defer statement, if you will. If this was Zig or Go, you had a defer statement which needs to be executed at the end. You could imagine that an interrupt would pause right here, no defer would be executed, and then you could re-enter into foo, thus clobbering your setup. So that's called reentrance, right? A reentrance problem is that. Okay, wow, dude, none of this stuff is all completely new to me. Except for like the basic ideas. The basic ideas I understand. Moreover, this Debian version suffers from the ASLR weakness described in the following great blog post by Justin Miller and Matthias Kraus, respectively. All right, they're right here. Toolchain necromancy, past mistakes haunting ASLR. Concretely, in this case, SSHD on I386. Gosh, I can't even read anymore. Too much reading today. I can feel the dyslexia really starting to want to come out. I'm refusing it. Re-entry is that other processes can foobar registers that aren't saved during interrupts. Yep. Concretely, in the case of SSHD I386, every memory mapping is randomized normally. SSHD's pi, the heap, most libraries, the stack. But glibc itself is always mapped to either the address this or at this. In other words, we can correctly guess glibc's address half the time. A small price to pay for defeating ASLR. In our exploit, we assume that glibc is mapped to address this because it is slightly more common than that. Our next question is, which code paths inside glibc's malloc function, if interrupted by sigalarm at the right time, leave the heap in an inconsistent state exploitable during one of the malloc calls inside of sigalarm handler? We found several interesting and surprising code paths, but the one we chose involves only relative sizes, not absolute addresses, unlike various code paths inside unlink chunk. For example, the difference might prove crucial for our future AMD 64 exploit. This code path inside malloc splits a large free chunk victim into 2 smaller chunks. The first chunk is returned to malloc's caller at line this, and the second chunk remainder is linked into an unsorted list of free chunks. Okay, so this is the back forward. This is the doubly linked list, arena, whatever allocation, something. We're looking at malloc time. All right, int malloc, let's go. If this code path is interrupted by sigalarm after line 4327. So let's look at 4327. So when we set the remainder, we've set the back and forward to be pointing to the same thing. But before 4339, which sets the head, then the remainder chunk of the split is already linked into the unsorted list of free chunks, line right here, but its size field, mchunk, is not yet initialized. If we're able to control its size field through leftovers from previous heap allocations, then we can make this remainder chunk larger and overlap with other chunks and therefore corrupt heap memory when this enlarged overlapping remainder chunk is eventually mallocated and written to inside SIG-alarm handler. Let's go. Our last question then is, given that we do not control anything, by the way, Matt, I am reading I hope you guys know I do read chat. This is the evil heap allocation fragmentation engine. Yeah, this is wild. It makes perfect sense. I just can't believe someone can do this. Like it makes sense from a theoretical standpoint, but from a practical standpoint, this seems effectively impossible in my head. Our last, especially since you get a chance once every 120 seconds, which just seems crazy. Our last question then is, given that we do not control anything about malloc calls inside of SIG-alarm handler, what can we overwrite in the heap to achieve arbitrary code execution before SSHD calls exit? Because TZ file read inside of SIG-alarm handler mallocates a file structure in the heap at line 166, and because file structures have a long history of abuse for arbitrary code execution, we decided to aim our heap corruption at this file structure. This is, however, easier said than done. Just like the rest of this article. Our heap corruption is very limited, and the file structure has been significantly hardened over the years by IO validate vtables and pointer demangle. For example, eventually we devised the following technique, which seems to be specific to the i386 glibc. The AMD64 glibc does not seem to use vtable offset at all. With our limited heap corruption, we overwrite the vtable offset field, a single signed char, of the TZ file read structure. The glibc's libio functions will therefore look for this file structure vtable pointer, a pointer to an array of function pointers, at a non-zero offset, our overwritten vtable offset, instead of the default 0 offset. Nice. So they offset it into their own little beautiful code, and then they let that be executed. Absolutely brilliant. We, attackers, can easily control this fake vtable pointers through leftovers from previous heap allocations because the file structure around this offset is not explicitly initialized by fopen. To pass the glibc's security checks, our fake vtable pointer must point somewhere into the libc IO vtable section. We decided to point it to the vtable for wide character streams, IO W file jumps, i.e. that exact number. We assume that the glibc is mapped to this address right here. Okay, yep. As a result, fread unlocked at line 186 calls the IO W write underflow instead of underscore IO file underflow, which calls a function pointer, function control. That's how I've always read it, functal function, that basically comes from the structure whose pointer, code CVT, is yet another field in the file structure. We attackers can easily control this code CVT pointer through leftovers from previous heap allocations. I like they use the word easily because this field is also a file structure is not explicitly initialized by fopen, which also allows us to control the function pointer. Okay. So this must be pointing into the above. I assume their namespace, the 128K of namespace, they are able to have their own code passed into that, and that's what's happening. In summary, by overwriting a single byte vtable offset of the file structure mallocated by fopen, we can call our own function pointer and execute arbitrary code during fread unlock. Practice. I wanted it perfect, no wrinkles in it. Okay, yeah. To mount this attack against SSHD privileged child, let us first imagine the following heap layout. Oh, we're getting into the juice now. This is the juice. Let's go. This is going to be a good one. The X's are barrier chunks that allow us to make holes in the heap. For example, small memory leaked chunks. All right. Shortly before SSHD receives the SIG alarm, we mallocated a 4K chunk that splits the large 8K KB chunks into two smaller chunks. All right. So they're messing with malloc at this point. If this, But if this malloc is interrupted by SIG alarm after line 43, but before this line, then the remainder chunk of this split is already linked into the unsorted list of free chunks. But its size field is under our control through leftovers of the previous heap allocations and is artificially enlarged to the remainder of the chunks. I know a lot of men that would be very happy if they could be artificially enlarged. All right, so that is cool. So they get one large chunk. They actually get a real remainder chunk and then artificially increase this to exceed over into the small hole. Okay. When SIG alarm handle calls syslog and hence tz file read, fopen mallocates the small hole for its file structure, and fread unlock mallocates the 4K read buffer, thereby splitting the enlarged remainder chunk into two, the 4K read buffer and small remainder chunk. There's the file offset right there. Look at that. There's the hole. Like, that's the separation. So they separate past the separator and they're able to go into the next one. We therefore override parts of the file structure with our internal header of this small remainder chunk. More precisely, we override the file's vtable offset with the third byte of the header's back field, which is a pointer to an unsorted list of free chunks. Right here. Yeah. Then, as we explained in the theory section, fread unlock calls IO wfwrite or wfile underflow instead of IO underflow, which calls our own function pointer through our own code CVT pointer and executes arbitrary code. Note, we have not yet explained how reliably go from controlled this pointer to controlled function pointer. We will do so, but we must first solve the more pressing problem. Non-zero values skill issues. Dude, the skill issue in this is so incredible. It's incredible. Indeed, we learned from our work an older SSH version that we will never win this signal handler race condition if our large race window contains only one small race window. Yeah, I mean, you would probably win, but I'd assume that the chance of winning is so large that it's impractical. So if we went, like what he's saying there is that if you remember the very beginning one, they had a single call that they were trying to break into, a single line or a single couple lines that they were trying to break into, but they realized if they used a different spot, they could get up to 24 of these same calls that happen over a larger race window. So they had this exploitable window, which was much larger compared to much smaller. And if this took approximately 10,000 times, which takes 1 to 2 days, theoretically, you could say this would take 240,000 times. Or in other words, 1 to 2 months. You would assume that this could theoretically at some point be exploitable. It's just so much larger. And if this thing has a default 600 second timeout, then this thing is like a year before you can get to it. The last packet that we should, by the way, that's also statistics. Statistics have no bearing into reality in some sense. Just because it's supposed to be 1 to 2 months does not mean it wouldn't take 6 months, right? It's the funny thing about statistics. When somebody says 1 in a million, it does not mean 1 in a million, right? It's just that's just never what that actually means, right? I know people say this all the time, and your head thinks of it that way, but that doesn't mean it's real. It's just not how you math. But people's brain thinks like that. So you're saying there's a chance? Yes. All right, let's look at this. The last packet we send into SSHD shortly before the delivery of the SIG alarm, this would be like the last byte, right, of the DE encryption, right, forces SSHD to perform the following sequence of mallocs. Malloc 4K, Malloc 304, Malloc 4K, Malloc 304, etc. Our first 4K splits the large hole 1 into 2. If this first split is interrupted by SIG alarm at the right time, then the fopen inside SIG alarm's handler mallocates the small hole 1 for the file structure, and we have achieved arbitrary code execution as explained above. If not, then we mallocated the small hole ourselves with our first Malloc 304. Then our second mallocation of 4K splits 2 larger holes into 2. If this second split is interrupted by SIG alarm at the right time, then fopen inside of SIG alarm mallocates the small hole 2 for its file structure, and we have achieved arbitrary code execution. Wow. If not, then we mallocate the small hole 2 ourselves with our second mallocate 304. We are able to make 27 pairs of such large and small holes into SSHD heap, 28 would exceed packet max size of 256 KB. Our large race window now contains 27 small race windows. Achieving this complex heap layout was extremely painful and time-consuming. Writing about it feels extremely painful. I cannot imagine writing the thing itself. But the two highlights are, we abuse SSH's public key parsing code to perform arbitrary sequences of mallocs and free calls. Yep. Cert parse right here. All right. It must be in which one? Cert free. Yep. So where's the cert free? Right there. Okay, yeah. We were unable to find memory leaks for our small barrier chunks. Instead, we used T-cache chunks, which are never really freed because their in-use bit is never cleared, to makeshift barrier chunks. To reliably achieve this heap layout, we sent 5 different public key packets to SSHD. Packets A to D can be sent long before SIG alarm. Most of packet E can also be sent long before SIG alarm, but its very last byte must be sent at the very last moment. Okay, there we go. A, we mallocated and freed a variety of T-cache chunks to ensure that the heap allocations that we do not control end up in these T-cache chunks, and we do not interfere with our carefully crafted heap layout. B, we mallocated and freed chunks of various sizes to make our 27 pairs of large and small holes and corresponding barrier chunks. C, we mallocated and freed 4 kilobyte chunks and 320 byte chunks to write the fake header to the large size field and our potentially enlarged remainder chunk into the middle of our large holes, write our fake footer into the potentially enlarged remainder chunk to the end of our small holes to pass the glibc security checks. We write our fake vtable and code CVT pointers into the small holes, which are potentially file structures. D, we mallocated and freed one very large string, nearly 256 KBs, to ensure that our large and small holes are removed from the unsorted list of free chunks and placed into their respective malloc bins. E, we force SSHD to perform our final sequence of malloc calls, right here, to open our 27 small race windows. Goodness gracious. Man. Attentive readers may have noticed that we still have not addressed, literally and figuratively, the problem of, in fact, code CVT is a pointer to a structure, is it IO convert, that contains a pointer to a structure, gconvert step that contains the function pointer that allows us to execute arbitrary code. To reliably control function through code convert, we simply point code convert to one of the libg's malloc bins, which conveniently contain a pointer to one of our free chunks in the heap, which contains their own function pointer to arbitrary glibc code. All of these glibc addresses are known to us because we assume that glibc is mapped to this address. Let's go. So this is how it does it. Yeah, this is the one this is the one they saved to the end, the very ending. Like you said, like that guy said. All right, timing. We are running out of time, the interrupters, as we live. As we implement this third exploit, it became clear that we could not simply reuse the timing strategy that we had used against 2 older OpenSSH versions. We were never winning this new race condition. Eventually, we understood why. It takes a long time, 10 milliseconds, for SSHD to parse our 5th and last public key. Yep, because it's... Okay, yeah. In other words, our large race window is too large. Our 27 small race windows are like needles in a haystack. The user-specified delay that was introduced recently, OpenSSH 7.8 P1, delays SSHD response to our last public key packet by up to 9 milliseconds and therefore destroys our feedback-based timing strategy. As a result, we developed a completely different timing strategy. From time to time, we send our last public key packet with a little mistake that produces an error response. Okay? Right before the call to SSH key from blob that parses our public key. From time to time, we send our last public key packet with another little mistake that produces an error response right here, right after the call to SSH key from blob that parses out our public key. The difference between those two response times is the time that it takes for the SSHD to parse our last public key, and this allows us to precisely time the transmission of our last packet to ensure that SSHD has time to parse our public key in the unprivileged child and then send it to the privileged child and start to parse it before we deliver the SIG alarm. Yep. Remember, I believe I did not too recently mention this whole problem. You're going to have this thing also fall into this. This is good. This is great. Mentioned? Oh, yeah, we mentioned, man. This makes perfect sense. Oh, my gosh. So they're actually using this as a timing. Since they could send a bad thing, they would know exactly how long this takes, and they can kind of build up the time these things take. Dude, C exploits are always nice. Dude, they're brilliant. With this change in strategy, dude, if they would have just wrote this with JavaScript, there would have been garbage collection, and thus you would have added a stochastic nature to this, thus never being able to actually be exploited. Duh, forehead. With this change in strategy, it takes 10,000 tries on average to win this race condition. With 100 connections max accepted per 120 seconds login grace time, it takes 3 to 4 hours on average to win the race condition and 6 to 8 hours to obtain a remote root shell. JS Heap spraying mentioned, absolutely. How about Rust? Towards an AMD 64 exploit. What's your plan for tomorrow? That's right. Take back the power. This is such, dude, this band is ridiculous. We decided to target Rocky Linux. Everybody's favorite Linux, Rocky Linux, a Red Hat Enterprise Linux 9 derivative. By the way, didn't Red Hat recently get dunked on by Oracle? I'm correct on that, right? Yeah. Yeah, I am. Yeah, but they got dunked on by Oracle. Or is it IBM? Either way, they got dunked on by either IBM or Oracle. I can't remember who owns Red Hat. I think it's Oracle that owns Red Hat, so it would have been IBM that does the dunking. But either way, imagine getting dunked on by either IBM or Oracle. It doesn't really matter which one that you get dunked on. Okay, IBM owns Red Hat. Okay, so then Oracle did the dunking. Okay, so Oracle did the dunking. I was right to begin with. Okay, but either way, imagine getting dunked on by Oracle. All right, Rocky Linux. Its OpenSSH version 8.7p1 is vulnerable to the signal handler race condition, and its glibc is always mapped to the multiples of 2 megabytes because of ASLR weakness discussed in the previous theory subsection, which makes partial pointer overwrites much more powerful. The syslog function, which is async signal unsafe, but is called by SSHD's SIG-alarm handler of the glibc version 234, internally calls open memstream, which mallocates a file structure in the heap, which also calls calloc and realloc and free, which gives us much needed freedom. With the heap corruption as a primitive 2 file structure mallocated in the heap and 21 fixed bits in the glibc addresses, we believe that the signal handler race condition is exploitable on AMD 64, probably not in 6 to 8 hours, but hopefully in less than 1 week. Only time will tell. Side note, we rediscovered the Ubuntu 2404 does not re-randomize the ASLR of its SSHD children. It is randomized only once at boot time. We tracked this down to patch below, which turns off the SSHD's re-exec flag. This is generally a bad idea, but in the particular case of this signal handler race condition, it prevents SSHD from being exploitable. The syslog inside the SIG-alarm handler does not call any of the malloc functions, because it is never the very first call to syslog. Defeated by lack of security. Let's go. The double defeat going on here. That's pretty cool. Patches and mitigation. The storm has come and gone. The interrupters. Good things. On June 6th, 2024, the signal handler race condition was fixed by a commit. This added to SSHD 8 to penalize particularly problematic client behaviors, which moved the async signal unsafe code from SIGD's SIG-alarm handler to SIGD's listener process, where it can be handled synchronously. Nice. Because this fix is a part of a large commit on top of an even larger defense in-depth commit. Start the process of splitting SSHD into separate binaries. It might prove difficult to backport. In that case, the signal handler race condition itself can be fixed by removing the commented out async handler unsafe code from the SSH SIGDI function. So all you have to do is just patch OpenSSH. Just hand roll your vendor and just uncommented it. There we go. Finally, if SSHD cannot be updated or recompiled, the signal handler race condition can be fixed by simply setting login grace time to 0. in the configuration file. This makes SSHD vulnerable to deal with with denial of service, the exhaustion of all Mac startup connections, but it makes it safe from the remote code execution. Sucks to suck. We thank OpenSSH's developers for their outstanding work and close collaboration on this release. We also thank Distro OpenWall, finally, for we dedicate this advisory to Sophia D. Antoine. I don't even know who that is. Is this a famous person? She passed away, CEO of Margin? Yeah, she died from getting hit by an SUV. Dang, that sucks. Well, there you go, Sophia. All right, timeline. We contacted OpenSSH's developers. Successful iterations of the patches and patch reviews followed. We contacted Distro's OpenWall. Coordinated release date. Let's go. Rip, yeah. Dude, rip. Damn. Well, that's nice that they have... it's very sweet of them to do a nice little dedication like that. Well, dang. That was an incredible read and just an amazing walkthrough. You know, whenever I read these things, it just highlights one exceptionally important thing. How dumb I am. That's what I feel like. You know, I'm out here writing basic network protocols, doing ASCII, and using Zig, and these people are hand-rolling heap configurations for malloc and offsetting into the SSHD and trying to time single-byte packets to cause SIG handlers to interrupt the free and malloc calls. Dang. Like, I mean, moral of the story, Pamela is not to be trusted. Never trust Pam. Same here. I'm so dumb, dude. It just makes me have... It just... Like, we've been doing a lot of security reading lately, from Polykill. This last one with the distributed harassment of service. Yeah, a DHoS. Now you know how we feel watching you program. Yeah. I'm very fast at Vim. Maybe I understand this Vim differentiation. Hey, if pound me too, dumb. Yeah, I know. Pound me too, dumb. Oh shit. You know, I'm not sure, Flip, if you can keep that one in. You know, like when I really think about it, this article was brunch for us key sheeters. This article was brunch. We just got brunched up. Pound you too. Hey, pound you too. Oh my gosh. I guess that's it. Leave it in or take it out, Flip. Up to you. The name. Hi, YouTube, Jen.